This is 6.2.11, page 5. In this example, we will continue with our previous example. In the previous example, we use n equals to 10. In this example, we use n equals to 100 to examine this equation. We see that when we have n equals to 10, then this is the fundamental period of this complex exponential, and for DTFS, n equals to 10 is sufficient. So why do we use n equals to 100, and what will change when n equals to 100? Remember that omega naught is equals to 2 pi over n, and in the original case of n equals to 10, then we have 0.2 pi. Now we have omega at 100. What will happen is that we are now using omega 100 means 2 pi over 100. So this is 0.02 pi. So every time we shift 1 k, we are shifting by 0.02 pi. In the past, we are shifting by 0.2 pi. So that is the difference. So in the DTFS representation now, the spike now is sitting at index k equals to 10. Because at k equals to 10, this point is k times 2 pi over 100, which is simply 10 times 2 pi divided by 200. So basically, again, it is 0 point is 2 pi divided by 10, so it's 0.2 pi. Okay, so as in the previous example, we're sitting at 0.2 pi for this amplitude with this phase. Same, now we are still sitting at 0.2 pi with this amplitude and this phase. Just there's more zeros there, it doesn't change a thing, because what we are seeing in the DTFS representation is saying that at 0.2 pi there's an amplitude of 3 with a phase shift of minus 0.5 pi and nothing else in between. So having more samples, n equals to 100 now, basically breaks our range of 0 to 2 pi into finer and finer frequency resolutions. That's why you see more points here, but the final representation does not change a thing. There is only still one spike at 0.2 pi from amplitude and phase. What has changed is the k. K is now 10 because we have broken the 0 to 2 pi into 100 pieces. So this is an important thing to note. When we change n from 100 to 10, the number of coefficients goes from 100 coefficients to 10 coefficients. What it means is that the resolutions under the horizontal axis have just changed. The representation of the information should have not, so which we see that it didn't. So the take-home message is that the omega naught is nothing but 2 pi over n, and whenever n changes, the omega naught changes. Now, something interesting occurs. Most of the time, you do not have a pure signal like what we have done, and it will not land directly on the frequency. So let's examine the same complex exponential using n equals to 101. In this case, that complex exponential doesn't lend itself to this bin. So what will happen now? You will now see that something strange happened. That frequency, which is sitting supposedly at 10 index, now is leaked to some neighbor a little bit, but nevertheless it shows that it leaks. And not only that, now you see that even though there is very little amplitude, it is greater than 1e minus 5. That is why you have all these phases over here. But I mean, you observe the phases associated with the magnitude, you realize that the magnitude is so small. So these phases doesn't mean a thing. The only thing that is interesting should be that phase associated with index 10. But here, maybe if you do not understand the word spectral leakage, you'll think that there is a amplitude at index 10 with some amplitude here. But since we have already generated only this real equation, this equation, which is a amplitude of 3 and 0.2 pi and a phase shift of minus 0.5 pi, there should be no other information here. This is nothing but a mathematical problem. It is a spectral leakage of this bin 10 into these others because there were no exact matching of the frequencies of these bins to this complex exponential 0.2 pi. Why? Because now omega naught is equals to 2 pi divided by 101, and there is no bin that will lend itself to 0.2 pi because omega naught is 2 pi divided by 101. So when you multiply by different k's, and k being an integer, it will never lend itself to 0.2 pi. Okay, so the take home message of spectral leakage is this: for real world signal, there is no chance that we would have exponentials lying exactly on the bin, and spectral leakage actually occurs all the time, and we have to learn how to interpret this spectral leakage. Thank you.